Hello. A lot of people here. So, I thought I'd begin this way. Can I have the Milicas up here? Melissa? How do you say this? Melissa. The two Melissas. The reason you are all here are these two Melissas. Can I get the two of you to stand like this? Both just like that. Just like, oh, good. Okay. Now, I want you to think of this span from here all the way to here as the age of the earth. Right? So, if this is the age of the earth, this is about 4.5 billion years. So, one hand is about 250 million. That would be 500 million, and then 1 billion to there, and then 2 billion to there, and 3 billion, 4 billion and a half, something like that. This is where, I'm such a privileged son of a gun, aren't I? This is where the Earth formed from the solar nebula, and this is today. Where were the dinosaurs? The dinosaurs formed here. They died there. Dinosaurs very recent, just within the last 100 million years or so. Very recent. When did life crawl out of the oceans? Right there. And during this entire period here, There was no life on land, no plants on land, no crawling life on land. But when did life begin? Life began here and stayed in the oceans for 3.5 billion years until it finally crawled out there. Yes, thank you. Well, I'd rather do it myself, thank you. Until it came out here. We, of course, humans, are right there. Thank you very much, both of you. So I'm here to talk to you about architecture, and you and I have about an hour to talk about this, so let's see how well this goes. But before we do that, do you have any idea how important software is? Let me give you a little clue here. How much software is running on your body at the moment? Now, let me show you how much software is running on my body at the moment. Of course, I have my iPhone here. How many processors are in this machine? I don't know how many. I've never done the analysis, but I can make a good guess. There's the main processor, of course, and there's probably a graphics processor. There's a GPS processor. It's probably a cell phone processor. So at least 4. And then, of course, the case has a processor in it because it's got the battery charger and Bluetooth connection, stuff like that. So a bunch of processors in this thing. And then I've got this. These are my iPods, or AirPods, whatever these things are called. And each one of the little earplugs has a processor in it, of which there are 2. And then, of course, the case has a processor in it. And, of course, I've got my Apple Watch, and that's got a processor in it. And they've strung me up to this device here that you're listening to me through. There's a processor in here, of course. I've got a load of processors just on my body. Now, how many do you have on your body? How many do you have near you? And then let's just ignore all that. Ignore all those computers. How many computers are running in the walls of this room? What about the speakers? Do the speakers have processors in them? Is there software running in each of the speakers? Probably. There's probably software running in each speaker because Nowadays, it is cheaper to filter out 50-cycle hum by using a little digital signal processor instead of using a capacitor and an inductor in normal circuitry. And that little digital signal processor would probably have some C code running in it doing fast Fourier transforms written by some 22-year-old at 3 in the morning. How about the cameras back there? They clearly have software in them. How about the exit signs? Do the exit signs have software running in them? Well, if there's a battery, and there ought to be for an exit sign, then there's probably something that will charge the battery, and that's probably got a little digital signal processor in it. So fine, there's software hidden in the walls of this room. But now go out on the road. How much software is running out on the road in each one of those cars? A modern car, and I'm not talking about a Tesla, a modern car has 100 million lines of code in it. That should scare the hell out of you. And most of that code, of course, is in the entertainment system and in the GPS system. But some of that code actually controls the motor and controls the brake. You'd like to think that when you touch the brake pedal, that there's a steel cable that goes all the way to the brake calipers, maybe through a hydraulic system to make the brake work. But nowadays, when you touch the brake pedal, it sends a signal to a computer, and that computer decides. There's an if statement in there. How many people have been killed because that if statement failed? And the answer to that is several dozen people have been killed by the failure of the software in the cars. There's a big payout to a number of companies. Toyota had to make a big payout because they killed several dozen people. And the reason they killed these people is that the software that controlled the engine failed, and the car would accelerate out of control and the brake wouldn't work. You and I are killing people. The software you and I write has the potential to kill people. Now, you and I did not get into this business because we want to kill people. Most programmers got into this business because they wrote an infinite loop once that printed their name, and they thought, oh, yes, oh, I want to do this for the rest of my life. But now we're killing people, and we're losing fortunes. Who heard the story of Knight Capital? Anybody heard that story, Knight Capital? Yeah, a few of you have heard the cap. I'm not going to tell you the whole story. Let me just tell you that some poor software programmer did one dumb thing and lost $450 million in 45 minutes. $450 million in 45 minutes gone in a flash. We are killing people. We are losing fortunes. Your grandmother, if you still have one, very likely interacts with a software system every minute of every day. Because in our society, in the Western world, it is almost impossible to do anything without interacting with a software system. You can't watch TV without interacting with the software system. You can't make a phone call. You can't use the microwave oven if you've got one. You can't use the dishwasher if you've got one. You can't use the sewing machine if you've got one, or the washing machine, or the dryer. You can't drive a car. You can't take an Uber. You can't take a Lyft. You can't take a taxi. You can't buy anything. You can't sell anything. You can't get an insurance claim. You can't buy a policy. You can't make a law. You can't enforce a law. Nothing can be done in the Western society without interacting with a software system. You and I rule the world. Other people think they rule the world, but then they write those rules down and give them to us, and we write the rules that execute in the machines that make everything in our society happen. our society does not rightly understand yet just how important we are, just how much they depend upon us. And we, programmers, don't quite understand that either. Every once in a while, someone will get a hint that, oh, maybe these programmers are actually pretty important. You think the airlines flying the 737 MAXs are thinking maybe the programmers are a little important right now? How about the guys at Volkswagen who tried to cheat the EPA, the California EPA, by cutting down their emissions whenever they were on a test stand, right? They think software is pretty important right now. So here's what's going to happen. One day, some poor software person is going to do some dumb thing and kill 10,000 people at a shot. Boom. And you know this is going to happen, and you can imagine what it might be. It's not that difficult. And when this occurs, the politicians of the world will rise up in righteous indignation, as they should, and they will point their fingers right at us. And you'd like to think, oh no, they're not going to point their fingers at us. They're going to point their fingers at my boss. They're going to point their fingers at my company. No, they won't. We saw what happened when the fingers pointed, when the CEO of Volkswagen North America testified before the American Congress. And the American congressman asked the CEO of Volkswagen North America, how could you have let this happen? How could you have cheated the California EPA with software? And the CEO of Volkswagen North America said, it was just a couple of software developers who did it for whatever reason. And the finger came right down where it belonged, right at the programmers. And with some justification, because it is our fingers on the keyboard. It is our minds writing that code. We are, in fact, responsible. And so when the politicians of the world point their finger at us and ask how we let 10,000 people die at a stroke, we'd better have an answer for them. Because if our answer is, oh, you know, my boss told me it had to be done on Tuesday, if that's the answer, then the politicians of the world will rise up and say, well, you guys are out of control, and we need to control you. We need to legislate. We need to pass laws. And they will tell us what languages we can use and what platforms we have to use and what books we have to read and what processes we have to use, what signatures we have to get, and we will become a heavily regulated industry. I'd like to get there before they do. I'd like for us, you and I, to figure out what our ethics are. What are the standards that we don't go below? What are the ethical rules that we follow? What are the disciplines that we adhere to? And how do we enforce them? And I want this to happen so that when the politicians of the world point their finger at us and ask us how this disaster could have happened, we can say, look, this was an accident. It was not due to our negligence. Here are our disciplines. Here's our standards. These are our ethics. This is how we enforce them. An accident, yes, but not because we were negligent. And we could not say that today. This may be the best time in the world to be a programmer. We have the maximum effect upon the world. It is a time of incredible demand. We cannot seem to get enough programmers. Look at how many programmers are sitting here in the room. There's 700 some odd programmers sitting here in this room. It's not enough. We need more and more and more. When I started programming, which was 52 years ago, how many programmers do you think there were in the world? 52 years ago, how many programmers were in the world? No, not 52. Thank you. Good answer. It would have been a better answer if you'd said 42. I don't know how many there were. It's probably a little more than 10,000. Probably a bit more than 10,000, but not an awful lot more than that. But let's go back a little bit further in time. Let's go all the way to 1946. 1946, how many programmers were there in the world? One. Alan Turing. He wrote the very first code that ran on the very first electronic computer, the automated computing engine in 1946. The day after that, there were a whole bunch of programmers, but he was the very first one. How many programmers are there now? In the world today, how many programmers are there? Well, it's definitely millions, but the question is whether it's tens of millions or whether it might be 100 million. It could be 100 million. It could be 100 million programmers in the world. It depends on whether you count the VBA programmers, but it could be 100 million programs. Now, let's just assume that it's 100 million, right? That's 10 to the, what? 10 to the 8th, 100 million. In 1946, it was 1. Today, it's 100 million. That was 73 years ago. In 73 years, we have grown from 1 to 100 million. Now, what kind of growth curve is that? Is it linear? It's obviously not linear. It must be exponential. All right, well, if it's exponential, we can assume that the base of the exponent was 2. And that would give us a doubling rate. So how many doublings does it take to get from 1 to 100 million in 76 years? Well, how many doublings does it take just to get from 1 to 100 million? Well, a million is 2 to the 20th, so that's 20 doublings. And 127 is 2 to the 7th, so maybe 27 doublings. 27 doublings from Alan Turing to today would give us 100 million programmers. And 27 doublings took place in 73 years. You can do the math. How many doublings per year is that? How many years per doubling is that? It's about 2 years. Does the number of programmers in the world double every 2 years? Probably not, because that first decade, there were more doublings than that. Right? The first day, it was Alan Turing. 2 days later, there were 10 programmers. A month later, there were 30 programmers. So in that first decade, the doubling rate was much higher. I believe right now the doubling rate is something on the order of 5 years. Every 5 years, the number of programmers in the world doubles. And this does not seem to be stopping. Now, at some point, it's going to have to stop, because we're going to run out of people. But, well, I mean, great, because 100 million, how many more do you have to go to get to 8 billion? Not that many. We're already at like 0.8% of the population, so that's pretty interesting. Do we really double every 5 years? All the evidence seems to suggest we do, but that has a fascinating implication. It means that half the programmers in the world have less than 5 years' experience. And this will always be true as long as we are doubling at a rate every 5 years. Half the programmers in the world will have less than 5 years' experience, which keeps our industry in a state of perpetual inexperience. We cannot grow, we cannot learn. Intellectually, we cannot grow because we are growing in population so fast. This is a good time to be a programmer because the demand is still high, the doubling rate is still high. Rejoice in the fact that you are a programmer. It's a very good career to have, and you will have a deep impact on society because society now depends on you for its existence. Doesn't quite understand that yet, but the day is coming. And therefore, one of the things that we should learn how to do well is to structure systems. The days are past when we can just kind of throw systems together and hope they work. We're going to have to learn how to do systems well. So, let's talk about architecture. What you're seeing on the screen is the directory structure of a system that my son gave to me, about 8-9 years ago. He wanted me to review it for him. And I looked at it and I said, that's a Rails application. I knew it was a Rails application. I'd seen Rails applications before. Who's done some Rails out here? Ruby on Rails. Look at that. Look at that. They're all in one little cluster over there. Ruby on Rails, big popular framework in the United States and Western Europe. Everybody wants to do Ruby on Rails. All the social networking companies want to do Ruby on Rails, or at least they did 5 years ago, not so much now. Because, you know, in software, everything comes in fads and popularity swings, and, you know, every 5 years you've got a brand new cohort of people joining the population of programmers, and they all want to do something new. So here they are. We got a Rails application, and I could recognize it just by the directory structure. And I'd seen many Rails applications before, but this time, something different occurred to me. And what occurred to me was that I could tell it was a Rails application. Why could I tell it was a Rails application? Why is the first thing I see Rails? That bothered me. I thought, wait a minute. The first thing I should see ought to be the reason the system exists. You know, why is this system here? What does this system do? But that's not what I saw. What I saw instead was the framework, and that bothered me. And I thought about it for a little while, and I realized that, wait a minute, Rails is a web framework. It's a framework about getting data on and off the web. And the web is a detail. And that was the first time I had put that idea together. The web is a detail. Now, that's hard for us to conceive of, right? Because the web seems to dominate us. The web is everything. We have to have a web system. We've got to do web stuff. Web. But the web is an I/O device. That's all it is, an I/O device. We can display things on a screen. We can get things from a keyboard. The web is an I/O device. And the one thing we learned way back in the 1960s was that we didn't want to know what I/O device we were using. We wanted our systems to not care what I/O device they were operating on. And therefore, we invented things like device independence. Who's done some Unix programming out here? Anybody done some Unix? Right? And if you're going to write something out to an I/O device, you don't write it out to that I/O device. You write it to standard out. And standard out is an abstraction. And the software doesn't know what it's writing to. Later on, when you execute it, you tell the operating system, oh, by the way, operating system, standard out is that printer over there. Device independence became very important. It was the way we protected ourselves from changes in I/O devices. And here we are, and the first thing I see on that directory structure is this I/O device, and I shouldn't be seeing the I/O device at all because the web is a detail. It's an I/O device. And so I started to consider architecture, and I got a few building plans out, some blueprints of buildings, and I realized that the building designs, like this one here, were not telling me what they were built out of. They were telling me what they were for. This is a library. You can tell it's a library, right? Because it's got bookshelves, and it's got desks, and it's got little computers, and there's an entry over there. It looks like a library, right? And if that one doesn't convince you, this one will. That's a church. The shape of the building is screaming at me what its intention is. I am a church. I am there to gather people together. Or I am a library. I am there to hold books. It is screaming at me what its intention is, and that's what the architecture of a building ought to do. And therefore, I thought, that's what the architecture of a software system ought to do. It ought to scream at me what its intention is, what it's for, what its requirements are, what its use cases are. Architecture is about intent, the shape of the system, the way its components are organized, the dependencies between those components. Is about the intent of the system, not about what it's built around. Now, I'm not the first guy to realize that. There was another guy who realized that a very long time ago. This guy's name is Ivar Jakobsen. And in 1992, Ivar Jakobsen wrote a very famous book. This one, Object-Oriented Software Engineering. Has anybody read that book? Has anybody out here read that book? There's one. Oh, there's 2, 3, 4, sort of. Well, that seems to be it. 4, maybe 5. Okay, there's a room of 700 people. 5 of you have read that book. That's a problem. Find that book, buy that book, read that book. And by the way, just offhand, there are a lot of extremely good books that were written before the year 2000 that you ought to buy and read and know. Who's got the Design Patterns book? Oh, look at that. Who's read it? Okay. Get the design. This, by the way, the Design Patterns book is probably the most important book on software written within the last 30 years. Get that book, read that book, understand that book. Don't let anybody tell you that it's gotten out of date. It hasn't gotten out of date. Don't let anybody tell you that, oh, well, now we're doing XYZ programming, and in XYZ programming, design patterns don't matter. Don't let anybody tell you that. That's nonsense. Get that book, read that book, understand what those patterns are so that you can speak intelligently about software design. How many of you have read The Structure and Interpretation of Computer Programs? Got one there, got one there, back there. I see just a few of you. The Structure and Interpretation of Computer Programs. That book will change your life. It's got so much code in it, and it will just change your life. It'll change the way you think about what code is and how it ought to be structured. Anyway, this is Ivar Jakobsen. Ivar Jakobsen wrote this book in 1992. And I want you to look at the subtitle of the book. The subtitle of the book says it is a use case-driven approach. Does anybody out there remember use cases? Look at that. Some people remember use cases. Good. The rest of you don't. Well, because we double every 5 years, and it's been 25. Right? So, use cases. Now, how many of you have heard the word user story? That's even more people, right? Okay. And then there are people who haven't heard that word either, which makes me wonder. But if you have not heard the word use case, but you have heard the word user story, a use case is a user story. Same thing. And what Jakobsen said was, use cases are significant architectural elements. They are the things that tell us the intention of the system. So they are important architectural elements in the shape of our software. This is what a use case might look like. Just a simple description of one small requirement. In this case, it's a create order use case. And notice that right at the top there, it specifies all the input data. Notice also that it doesn't specify the input data in any detail. It's just kind of a high-level abstraction of the input data. It says, there's a customer ID. I don't know what form the customer ID is in, but it's there. And there's a customer contact info. Don't know what the form is. That's okay. Shipment destination, shipment mechanism, payment information. Just the names of the data without any details. And the reason there aren't any details is that this is written at a time when the details are not important. One of the biggest mistakes that programmers make is that they assert detail far too soon. Programmers are detail managers. Did you know that you were a detail manager? That's your job. Your job is to manage the most hideous details that anyone has ever managed ever before. How many of you within the last year have written an if statement that checks to see if a text file has lines that end in \r or \n? Who's written that if statement in the last couple of years? Now, that's just the most hideous possible detail. But you and I have to deal with stuff like that. We deal with all the worst possible details. You and I are detail managers, but we make a mistake. We get ahead of ourselves. We assert the details too soon. So here's a use case where all the details are abstracted away. We're not going to think about them yet. We'll think about them later, just not yet. And then after the input data, we see the primary course, and the primary course shows the steps in the procedure for processing this use case. And the steps are fairly simple. Order clerk issues create order command with the above data. That's actually not even part of the use case. That's just how the use case gets kicked off. And the system validates all the data. I don't tell you how it validates all the data. That's a detail. We'll deal with that later. But we do have to validate it. System creates an order and determines the order ID. Of course, I don't tell you how that happens. Probably it's a database activity, but I'm not going to say that here because that's a detail. System delivers order ID to clerk, probably on a web page, but I'm not going to say that here because that's a detail. It's a nice, concise description of the inputs and the outputs and the processing steps without mentioning any of the details. That's what a use case is. And then Jakobson, in his book, made this observation. He said that is an object. A use case is an object. You can write the code for it. Even though you don't know the details yet, you can write the code for it because we, programmers, deal with languages that can abstract things. So we can write very abstract code, real code that would really execute, that would deal with the abstract notion of a use case. Now, I like to call the objects that represent use cases interactors. People have said, well, Bob, you should have called them use cases, and maybe that's a good point. But I didn't. I called them interactors, so okay, I'm stuck with that name. Jakobson called them control objects, and that's a problem because of model view controller. People get confused with model view controller, so I thought it would be better not to call them control objects. An interactor is a business rule, but it's a very special kind of business rule. It's an application-specific business rule. There are two kinds, broad category, two kinds of business rules. There are the business rules that have nothing to do with the automation. These are the business rules that the business would still use even if there were no computer. So for example, let's say you're doing a banking system. Interest calculations would be done whether or not you've got a computer, right? Doesn't matter. So those are application-independent business rules. But then there are other business rules that are all about the automation. And use cases are all about the automation. They're application-specific. They're not independent of the application. The only reason they exist is because we are automating. The second kind of business rule, Jakobson called an entity. Entities contain the application-independent business rules, the interest calculations, the rules that would be done even if there were no automation. And the interactors and the entities are kept separate because it's necessary to keep that kind of stuff separate in your code. You don't want to have application-specific business rules that are coupled tightly to application-independent business rules. You want to maintain that separation. And then finally, Jakobson said, you got to get data in and out of those things, so we're going to create some boundary interfaces. And if you look carefully at these boundary interfaces, you'll see that there's two different kinds of arrows there. The open arrow is a using relationship. The closed arrow is an inheritance relationship or an extends relationship or an implements relationship. The two boundaries are interfaces very much like Java-style interfaces. What languages are you guys using? Who's using Java? Look at that, a lot of Java people. Who's using C#? Wow, a lot of people using C# too. Same language, by the way. Right? Microsoft just stole Java. Just outright stole it. Does anybody remember Visual J++? Anybody? Long, yeah, see people, they're really old. They remember Visual J++, right? And then Sun Microsystems said, hey, Microsoft, you can't do that, that's ours. And Microsoft said, oh, you know, you're right. And they changed a keyword into a colon and turned it into C#. Same language. Now, they've diverged since a little bit, although even today you can put up a page of Java and a page of .NET and not see the difference. So, what else do we have, by the way? Who's doing Python? Look at that, we've got some Python programmers, yeah. And we already talked about the Ruby programmers over there. Who's doing F#? Nobody doing F#. Functional language. How about Scala? There's a couple of Scala people. Oh, good, functional language. Okay, now the interesting ones. Who's doing Objective-C? Look at that. iPhone people, way out of date. Who's doing Swift? Oh, look at that, same people. Fascinating. Anybody doing Go? Who's doing Go? Ooh, they got the Go people. Big cluster of them right here. Go. Hey, I'll give you a little hint about Go. If you've been doing Java or .NET for a while, you have gotten used to that quarter-second startup time of the virtual machine. You tell it to go, and there's a little heartbeat, and then it goes. Right? And when you're doing Golang, that's not there. That's not there. You tell it to go, bam. And you don't have time to even think. And who's doing test-driven development? Let me see hands. Test, right? Oh, we need to work on you guys. You're not doing test-driven development anywhere near enough. Come on, that's a discipline. We have to do that discipline. Otherwise, when the politicians point their finger at us, we're not going to have any excuse. Did you guys write tests? Well, we didn't know we were supposed to. Because my boss said it had to be done really, really soon. And you know, I did write like one test, but I lost it. You're laughing, aren't you? Yeah. Okay, yeah, we have to come back and work on you. So those of you lucky people who have done test-driven development, if you have done it in Java, you will know that you push the test button, and then there's this little pause, and then you see the green bar sweep across, and life is good, and everything passes. And when you do this in Go, you push the test button, boom. Go is one of those languages that lets you see how fast the machine actually is. Java and C# hide that from you in a kind of sad way. So keep that in mind. Anyway, those boundaries are interfaces in whatever language you want, Java, C#, whatever. Those are the interfaces. And you can see how data can come in through that lower boundary. That lower boundary would accept data in, and then it would be implemented by the interactor. So that's an inheritance relationship. And the top boundary, that's an output boundary. The interactor uses that. Notice also that only the interactor talks to those boundaries. Right? The entities don't know about the outside world. The entities just believe they live in their own little world. They are the pure business rules. The interactors are the ones that coordinate the execution of the entities, coordinate the acceptance of input and the delivery of output. Now we're going to walk through a typical scenario. We got a little dude down there, and he's about to push the submit button on a web page. I didn't tell you it was a web page. I called it the delivery mechanism. It might not even be a web page. Maybe it's some other kind of interface. Maybe it's a console interface, or maybe it's a desktop, or maybe it's a service-oriented architecture port. Who's doing service-oriented architecture? Look at that, right? Who's doing microservices? Oh, same thing, guys. Same thing, microservices, service-oriented architecture. And you got to ask yourself why you're doing this. Why are you doing microservices? Well, because it's cool. Because like everybody else is doing it, so we have to do it too. Make sure you understand why you are doing microservices. I won't say any more today, maybe later. Anyway, here we are. This is the delivery mechanism, probably the web. And the user hits the submit button. And now the delivery mechanism gathers the data from the input device. This is probably the web controller, by the way. Gets all the data from the form or whatever. And it moves that data into a data structure that I call a request model. That data structure is a raw data structure. It doesn't know anything about the web. It doesn't derive from any framework. If you're doing Java, this is a plain old Java object. There's no dependencies at all. It doesn't have any methods. It's just a bunch of public fields. It's a data structure. And it gets passed into the input boundary so that the interactor can see it. The interactor begins to inspect it. It understands what its interaction is supposed to be by looking at the request model, and then it controls the dance of the entities. It feeds data to all the application-independent business rules, the entities, makes them do their work. And then when it's done with that, it reverses the flow and starts to pull data back out of the entities. These are the answers that we want. And it gathers those answers together, and the interactor builds a result model. The result model is just a raw data structure. If you're doing .NET, it's a plain old C# object. There's no dependence on any kind of framework or anything like that. Just a nice little data structure. That data structure gets passed out through the output boundary, through the delivery mechanism where it's displayed on the screen to the user. Simple request-response interface. Nicely isolated so that the application-independent business rules are separated from the application-dependent business rules, and there's a nice boundary, and then that is attached to the delivery mechanism, which can't know anything about the other side. Can I test the interactor? Can I test that? Can I test it without the web server running? Could I test that interactor at 30,000 feet over the Atlantic sipping a gin and tonic on my laptop? Well, you spill gin and tonics on your laptop. It's not a good idea. But I could. I could test that interactor without any of the rest of the system running. This is always a goal, by the way. You want to be able to run tests on parts of your system without the rest of the system running. You want to be able to test your systems in parts. And this allows me to do that. Now, what about Model View Controller? You've all been doing Model View Controller for God knows how long. What does it look like? This is the guy who invented Model View Controller back in the 1970s. His name, I'm going to butcher because I can't speak Danish, is Trygve Renskaug. Now, that's a butchered pronunciation, but it's the best I can do. I met him once. I was at a conference in Norway, and I went up to the speaker lounge, and I was looking for a place to plug in my laptop, and this grizzled old guy hands me a power strip, and I reach out and I took the power strip, and I looked up at him, and the blood drains from my face, and oh my God, that's Trygve Renskaug. And as I took this from him, our fingers brushed, just briefly. And I don't wash those fingers. Way back in the 70s, Trygve Renskaug came up with this simple idea. You've got a model, that's just a business rule, a real simple business rule, and it doesn't know how it gets its input, and it doesn't know how it gets its output. It's just a business rule. And there's a view up there, and that view knows how to display the contents of the model out to the outside world somehow. And there's a controller down there, and the controller knows how to accept input from the outside world and hand it into the model. A simple input, process, output kind of design pattern. And when we were doing this, we used to do this in Smalltalk. That's where it was invented for the language Smalltalk. And when we did this, we would have model view controllers for every little widget on the screen. There was a model view controller for a button, model view controller for a checkbox, model view controller for a menu. We did not have a model for the whole screen. We just had little individual models for all the little bits. This was a design pattern that we used in the small, not in the large. Now, this has gotten bastardized over the years so that now it looks something like this. This is how we do model view controller on the web. You probably have model view controller web frameworks that you've used. And you've got these controllers out there, and they take all the input from the web by some magic, and then they fire off a bunch of commands to the business objects, which are the models, and then eventually they hand control over to the views, and the views gather all the data out of the business objects and put it on the screen. And the problem with this, of course, is that all those lines cross. And programmers forget where they're supposed to put stuff. So you'll wind up with with view-like code in the business objects. And you'll wind up with business object-like code in the controllers because there's no firm boundaries. So here's the model I prefer. This is the Jacobsonian interactor model. And what we're going to explore here is how the data gets out to the web or to whatever your I/O device is. So it begins at the interactor here. The interactor has created the response model, and you can see that there. And the interactor is going to send that response model out through the output boundary. Now look what implements the output boundary. There's a little object there called a presenter. And the job of the presenter is to take the data in the response model and reformat it so that it's displayable. If you've got a date in the response model, that date is just a date object. Right? By the time the presenter gets it, it will convert it into a string and put it in the view model. And that string will be formatted for whatever your locale is. If there is a money object in the response model, it'll just be a raw money object. By the time the presenter gets it, it will convert it into a string with the right decimal places and the right currency marks and so on. If there's some kind of a grid that you want to display, the presenter will organize the data from the response model into the view model in a grid form. If there are buttons on the screen, the presenter will know the names of those buttons and will put those names as strings into the view model. If those buttons need to be gray, the presenter will make sure that there's a Boolean in the view model that says gray out this button. Any decision at all that can be made about the screen is made by the presenter. And it's loaded into this view model data structure, which is just another data structure which holds mostly strings. And then the view is this faded thing that barely exists. All it does is copy the strings onto the screen and walk away. Can you test that presenter? You can. You pass it a request, you pass it the response model, and you look at the view model. Do you have to have the web server running while you test it? No, you don't. You can test the system in parts. Test the system in parts. This is kind of what the whole thing looks like from the interactor over. Got controllers off to one side. They feed the request models into the interactors through the boundaries. I don't show the entities out here, but eventually the interactor feeds the response models back through the boundaries out to the presenter. And you see this double black line there? That's an architectural boundary. That's an architectural boundary, and notice that all the dependencies cross that architectural boundary in one direction. That's the key to an architectural boundary. Whenever you have an architectural boundary, you want every dependency to cross it in one direction, and the direction itself is critical. All the dependencies point in the direction of the higher level policy. The stuff on the left, the controller and the presenter, is low-level stuff, detail stuff. The stuff on the right, that's high-level stuff. That's business rules. Look at the business rules over to the right. They don't know anything about the details. They don't know anything off to the left there. They have no dependencies going that direction. You could take those business rules and put them in a DLL or a jar file and deploy them independently of the web. The web, which is off to the left, that's a plug-in. That's a plug-in to the business rules. And if you can plug the web into the business rules, you can unplug the web from the business rules, plug something else in if you want, some kind of a console interface. You don't want to plug a console interface in, plug a service-oriented architecture interface in. You can plug anything you want into that. But you know what you're really going to plug into it? A bunch of tests, because that's also your test boundary. That's where you're going to be writing integration tests into the system. Yeah, but what about the database? Well, I've got 11 minutes. I can talk about the database. Might take me a little longer than that. Anybody have this view of the database? The database is the great God in the center of our system. All hail the database. All other things bow down to the database. The database is everything. This is the wrong view. We don't want to think of the database this way because the database is an I/O device. The database is an I/O device. It's a place we stick data. It's not some great center of the system. Who would benefit from telling us that the database is the great God in the center of the system? Who would most benefit from that? Well, you say the DBAs, and you're right, of course, the DBAs. Do we have any DBAs in the room? Okay, I'm safe. Good. Of course the DBAs do, but it's not the DBAs, because who created DBAs in the first place? Does anybody know where that job description came from? Who created the very concept of DBAs? Database companies. The people who sold databases to companies came up with the job description of the DBA. They told the people they sold the databases to, you know, you got to have people who can administer these databases too. And they have to have control. And they have to have all the passwords. And by doing so, the database companies created a very loyal little army of people that held all the keys. Now, what do you think the argument was? How do you convince a bunch of executives that they've got to buy a really expensive database? Get this, right? Salesman goes into a CEO. All right, are you protecting your data assets? What a great word. Data asset, right? Huh. And the CEO goes, I didn't know I had any data assets. Oh, yes, you do. And our system will protect your data assets. All you need to do is buy our system. It was a wonderful scam, and it took place in the 70s and the 80s, and it pervaded databases everywhere. And it made them the center of systems, except for those architects and designers who knew all along that databases were actually details and I/O devices, and we should not be centering our systems around them. And so what do? Well, we put them behind an architectural boundary. There you go. There's the database down there, that red block down there. We got some nice architectural boundary crossing the screen from left to right. Here's the interactor. The interactor knows that it has to interact with something that stores the data. It doesn't know that it's a database, has no idea, like doesn't know that it's Oracle or whatever you might be using. It just knows that it has to interact with something that saves data. And it does that interaction through that interface there called an entity gateway. The entity gateway has methods, one for each query you want to do. So for example, let's say you want to query all the employees that were hired after 1972, because they're old now and you need to fire them, right? So you're going to query the database for all the employees hired before 1972. You would have a method in the entity gateway which said, get employees hired before, and then you'd pass in a date. And you do that for every query in your system, so that your entity gateways list every possible query operation you need to make. Then you implement that down below the line, and the database down here becomes a plug-in to the business rules. Where's the SQL? Anybody out there write SQL? Who writes SQL? I'm sorry. It's a shame that you have to write SQL. SQL is a fine language if you are sitting at a console and you want to query a database. It is not a good programming interface. It possibly is the worst possible programming interface because programmers don't want to pass strings into an API. They want to call functions into an API. And wouldn't it be nice if all of our databases had an actual API that we could call functions on instead of trying to construct horrible select where strings that fits some nasty syntax? And so what do? We make our ORMs. We get the whole problem away from us. We use ORMs. Where's the ORM in this? Down here. No ORMs above the line, no SQL above the line, nothing above the line except the business rules. If you're using an ORM, you put it below the line. But you don't have to use an ORM, of course, because you could implement that entity gateway with anything you want. You want to use some NoSQL database? You could use a NoSQL database right there. Business rules aren't going to know. Oh, and by the way, if you're running tests, You can rip the database out completely and just put a bunch of stubs down in there. And your tests will go really fast. I'm going to tell you a little story. And after that story, we'll be done. And then there will be some time for questions. The story goes like this. This is the story of an application called Fitness. Has anybody used Fitness? Oh, several of you have. Good. Good to hear. Fitness is a wiki that my son and I wrote 20 years ago. It's also a testing tool. It's for integration level testing. It allows business people and QA people to write tables on wiki pages, and those tables specify both input data and expected output data, and then the tool figures out how to call the system being tested with the input data and compare the output data, and we get nice little tests that way. Now, I'm not going to describe that in any more detail. I want to talk about how this was done. We sat down, the day that we decided to do this, we sat down and said, okay, this is a wiki. And since it's a wiki, we're going to need a place to store wiki pages. That ought to be in a database. Well, what database should we use? And we said, well, we want this to be open source, and there's only one open source relational database we can use, so let's use MySQL. We said, okay, we'll use MySQL. And we realized, okay, well, that means we need to come up with the schema of the database, and we have to get a license for it, and we got to power it up and figure it all out. And somebody said, well, wait, you don't have to do that yet, because there's another problem you've got to solve first. And that problem is, you've got to translate the wiki markup language to HTML. Now, that's a big problem all by itself, and we thought, okay, let's do that first. And so we came up with this mock object here, this wiki page interface, which had a toHTML method and a save method. And then we created a mock of that, and the mock would do the conversion from wiki markup to HTML. It allowed us to do that, but it mocked out the save method. And for about 3 months, we just worked away. Now, we were doing test-driven development. So, little test, little code, little test, little code, little test, little code for 3 months, getting all this stuff to work. And we got it all to work. And we can convert wiki text into HTML. That was great. And finally, we said, okay, well, now we've got to be able to save these pages somewhere. So let's go get MySQL. And somebody said, well, we don't need to get MySQL yet because we could just take the pages and stick them in a hash table in memory. And that would kind of act like a database. And so we thought, that's not a bad idea. So we created this in-memory page, derivative of the wiki page, and it just put all the pages in a hash table in memory. And that way, we could keep writing tests, making it pass, writing tests, making it pass. Now, of course, we had pages that we could save temporarily. And we could implement all kinds of very interesting features. We actually worked a year that way. We got the whole system working. All the wiki stuff and the linking stuff and the multiple pages and the hierarchy of pages and the testing application stuff, all that stuff worked, but we couldn't save anything, which was a bit annoying. Towards the end of this period, we said, all right, look, this business of keeping everything in memory is getting old. We need to be able to save this stuff. Let's go get MySQL. And Michael Feathers was there at the time, and Michael Feathers said, well, you don't really have to do that yet, because you could just take that hash table and write it out to flat files. That'd be really easy. And so he actually came back a day later with the whole thing written out into flat files, and we just kept on working that way. Make a little test, make it pass, write a test, make it pass. All of a sudden, we had persistence. We took it on the road. We showed people, hey, this is Fitness, and people started using it. And more people started using it, and we were using it, and it got more and more popular. About 3 months later, we realized we didn't need that database at all. We never put that damn database in there. Well, a year later, we did. A year later, right? A customer comes to us, and that customer says, we got to have it in a database. And we said, well, why? Right? Because it works fine now. It's fast, it's easy, and you can actually check your pages into source code control. That'd be really tough to do with a database, so it's better this way, isn't it? He said, yeah, it's better, but we got to have it in a database anyway because our CEO says we've got to protect our data assets. And we said, well, I guess you can't fight City Hall. So we showed him the original design here, which is this design, that one. And we said, well, look, all you have to do is make another derivative, sort of like file system page, call it MySQL page if you want. Just implement those functions in there, and you'll be able to get it into MySQL. He came back a couple of days later with the whole thing working in MySQL. We used to ship that as a plugin, but nobody used it, so we stopped. He even stopped a year later because they changed management. And the moral of that story is this. We took what you would think of as a critical architectural decision, the database itself, and we deferred it, and we deferred it, and we deferred it right off the end of the project. A good architecture is an architecture that allows big decisions to be delayed and deferred, not made. Delayed and deferred. You defer them until the last responsible moment, the moment when you've got the most information to make or not make that decision. You do not want to make all these decisions early. Again, this gets back to the whole idea of too much detail too early. Push those decisions out, which you can do by controlling the shape of the system and the direction of the dependencies in that system. A good architecture minimizes the number of decisions not made, maximizes the number of decisions not made. And with that, I'll open this up for some questions. Anybody got any questions? Do we have microphones for the people who have questions? Looks like we do. We got runners for the microphone. So who's got a question? Oh. Ah. Yep, there's one.
Hi, hello. I'm interested in which parts of the application we need to do unit tests, to do test-driven development. On which parts? And what about code coverage?
Which parts of the application do you need to unit test? And what about code coverage? You only test the parts of the application that you want to work? And what's the coverage? What kind of coverage should you have? Who's got a limit? Who's got a goal, coverage goal of maybe like 80%? Got an 80% coverage goal. We've got it. That means it's okay if 20% of the system doesn't work. There's only one coverage goal that makes any sense. That's 100%. You can't achieve 100%. It's an asymptotic goal, but it doesn't mean you ever stop trying. So you're always trying to push closer and closer to 100%. Now, I was a little bit flippant there. I said earlier on that you only test the things you want to work. Okay, that's true, but there are parts of systems that are very, very difficult to test. In particular, those are GUIs. And GUI is just an example of other kinds of things that are hard to test. Anything at the outer boundary of the system is hard to test because you can't get code on the other side of it. I can't get code on the other side of the pixels on the screen. I can't test the pixels on the screen easily. There are strategies for that, but they're hardly worth doing. So my particular discipline is to get as much code out of the GUI as possible, test it, and then the last few bits of code that touch the screen I simply don't test, at least with unit tests. I test them with my eyes. A good example of that is CSS. Do you test your CSS, right? And I don't, right? Because I just sit there and fiddle with the CSS until it looks right. And that's probably about it. So you cannot test things that are at the very edge of the system. And it's also very difficult to test things if you don't know the answer. If you've got a function in the system that you need to implement, but you don't know what it's supposed to do, it's really hard to write a test. So, for example, let's say that you're doing a big finite element analysis. You're analyzing the airflow over a wing. And the very purpose for this is to get the answer. You don't know the answer. You don't know what the airflow over the wing is. So you can't write a test for this. But you can write tests for all the little bits. You can write a test for each finite element. You can make sure that the airflow over a small rectangle or a small triangle behaves properly. You just can't test the larger thing. You're going to have to trust the larger thing. Anybody else? Question? Looks like we got one over here. 6 minutes left.
Hello.
Hello.
So how do you communicate intent with the folder structure?
How do we
communicate intent?
Intent.
Yes, of a software that we are developing with a folder structure.
How do you communicate the intent of what you're building with a folder structure? Going back to my very first slide.
Exactly.
Wouldn't it be nice if there were a folder up there called use cases? Wouldn't it be nice if in each one of those, in that use case folder, there was a class for each use case in the system? Wouldn't that be nice? That would be one way to do that. Wouldn't it be nice if we had a folder for all of the entities, all of the application-independent business rules, and we could see each one of those? That's what I want. I want to take those objects and promote them to the top level so that at the top level of the system, you can see the use cases and the entities and know what this system does. And the one I showed you, that one that was Rails, what you saw at the top of that was Rails. This is a Rails app. You didn't know what it did. You could have found out by looking deeper and deeper. But I don't want to have to look deeper and deeper. I want to know at the top. This is an accounting system. Next. We got questions behind you there. There's one back there. There's a couple over there. Doesn't want to let go of the microphone, do you? You want to keep that microphone, don't you?
Yeah.
Huh?
Just continuation.
Follow-up question?
Yes.
Yeah.
Because there are limits to the frameworks used or the languages used.
Yes.
So how do you go around them?
How do you go around it? So how do you deal with a framework? Let me tell you a little thing about frameworks. Yeah. I love giving the camera guy a hard time. All right. Because he's got to track me, and I'm a tough son of a gun to track. So that guy's sweating more than I am. Frameworks are wonderful things. You can get a lot done with a framework. You get a framework like Spring or Rails or JSF or JPA, any of those neat little frameworks. Wonderful. Angular, lovely things. But the author of the framework does not know you and does not care about you. The author of the framework does not understand your problems, is not writing code to solve your problems. They are writing code to solve their problems. When you use a framework, you make an enormous commitment to that framework. You bind your code to it. In the very worst case, you derive from base classes in the framework. The framework author makes no such commitment to you. It is a terribly asymmetric relationship. And as an architect, if you are an architect or if you're a lead designer, you must be very skeptical of that relationship because you should be thinking that this framework is out to screw me. You should be looking very, very carefully at how much you bind to it. Read the directions, you know, the documents that the framework author writes. Read those directions, but do not follow those directions because the directions that the framework author writes will tell you to couple to the framework intimately because he loves the framework. You don't have to. So then what you do is you put the framework behind an architectural boundary. You draw those black lines again and you put the framework behind that boundary and you use it, but you use it in a very careful way so that one day, when that framework no longer satisfies your needs, you will have some options. How many of you have used a framework, built it into your system, coupled it so tightly into your system, only to find out 2 years later there's a much better framework out there, but you have no way to get it in there because you are so inextricably bound? How many of you have had this problem? You start out with a framework and it's wonderful. It's wonderful. It lets you go fast. But then a few months later, you want to do something that the framework doesn't want to let you do. And the framework starts to fight you. And the more you want to do these secondary and tertiary things that aren't what the framework allows, the more it fights you. And in the end, the framework costs you more than it gives you. You have to be careful about frameworks. They're lovely things, they're wonderful things. They are not pure good. They are tools, and like any tool, you better know how to use them and how to keep yourself at some distance from them. How many of you are doing dependency injection? Oh, look at that. Everybody's doing dependency injection. That's cool. How many of you inject hundreds of things into your applications? Oh, only a couple of you are doing that. Who's using Spring? Well, who's got add auto wireds everywhere? Add auto wired here and there scattered through your code. I don't want to see that stuff. I don't want to see add auto wired in all your business objects, right? Because if you put those in your business objects, you have coupled your business objects to Spring. Why do your business objects have to know anything about Spring? You want to use a dependency injection framework, that's fine. But inject the dependencies into a safe place behind an architectural boundary and then pass those objects into the rest of your system through normal means. And probably you should not be injecting any more than a dozen things. I've got 42 seconds.
What is your attitude, the point
good.
of
My
view
attitude's good.
about that we don't need integrational tests, for example, with database? Because in that case, we just test framework. We could mock all things which come from database.
I think that's probably a good idea. I mock out the database for just about everything. I will test the individual queries just to make sure that I've formatted the queries correctly. But there's not much need to test a database if that database is something you've purchased. So I'll just set that aside and mock it out. Is that your answer? Good? Okay, I think we're done. The time is 0 on my timer. Thank you all for your attention.